All right, we're back. We're on page 6, notes 1, Calc D, talking about multivariable stuff. It all starts out with vectors in 3 dimensions. So you got to know a lot of stuff about vectors in 3 dimensions. Let's see if we can do that. So we're going to talk about something called the cross product. So we've got a scalar multiplication, right? Take a vector, multiply by a scalar, you get a vector back that is scaled, either up or down, depending on if the absolute value of the scalar is greater than 1 or less than 1. You can get a dot product, right? The dot product is a scalar, right? The result of taking a dot product will give you a scalar, and then that can tell you something about the angle between the vectors, can tell you it's related to finding the component, like a lot of stuff there. The next thing we're going to do is talk about a cross product. So it's still not vector multiplication. There's really nothing that is vector multiplication. All 3 of them are good options. In fact, all 3 of them use the 3 different forms of multiplication, right? So if you have a vector v and u, let's say, so u and v, excuse me, and then a scalar c, right? So scalar multiplication would be c times v. Dot product would be u dot v. And then the cross product would be u cross v. So I've always really liked that the 3 types of things that might be considered vector multiplication use kind of the 3 different notations for multiplication that we have like throughout our math career. I think that's kind of neat. But yet none of them are really vector multiplication. So what are we trying to answer with the cross product? Well, the cross product, what we're trying to answer, remember we're in 3 dimensions now, we're trying to answer the question, what is a non-zero vector that is orthogonal or at right angles to 2 particular vectors, right? So if we just have one vector and we want a vector orthogonal to it, we can use the dot product, right? Because if the dot product is 0, then the vectors are orthogonal. Here we want a single vector that is orthogonal to 2 given vectors. So what we're going to do is we're going to see if we can just work it out. So we want to find any non-zero vector that is perpendicular to both the vectors 2, -1, 3, and 1, 2, 5. We're going to use a calculator to speed it up. So what I'm going to do initially is I'm just going to like make a vector. So let v equal, let's say, I don't know, a comma b comma 1 be orthogonal to, should we name these? Let's name these a and b. No, let's name them u. What would I name that? Let's change this to u, and then I'll use v and w. U, v, and w. So u is going to be orthogonal to v and w. So what does that mean? Well, that just means that u dot v equals 0 and u dot w equals 0. So I'm going to use a calculator to solve for a and b and see what I get. I'm going to also, I'm going to do it again and say that u is equal to, I don't know, 1 comma b comma c, just to see what happens. And then also, maybe I'll do it a third time where I let u equal a, b, c. All right, and we just want to like see, we're looking for, so all of them are going to have the same system. So I'm just going to copy that. Duplicate u, go to the calculator and see what we can do. So on the calculator, I got to share it. Hold on, sharing. This is the idea, right? So we could do this. Like you can approach each problem as its own special, unique thing where you're going to like solve it, right, for a particular problem. That's not really how you want to do things in math. You want to come up with generalizations. So we'll see if we can do that. W is 1, 2, 5. All right, so I want to solve. So I'm going to do, well, this is, if I run the handheld, I do menu 3, 7, system of equations. It's 2 equations. The 2 unknowns are going to be a and b for this particular thing. And I want to do the dot product, which is menu 7, C3 of u and v equals 0 and that the dot product of u and w equals 0, and I need to know what a and b are, right? So I get negative 11/5, negative 7/5, and then 1, right? Because that's this. So if I do this, and that's fine, but like, why not multiply by 5? You know, like, why use these fractions? So I've multiplied by 5. Let's try the problem again. I'm going to all I need to do is redefine this. Well, all. I'm going to make it 1, b is b, and then c. And I'm going to try this again. So we're going to solve this time for b and c. I don't know what'll happen if I leave it the way it is. I mean, we could find out. So now do such that this, why not? Let's multiply by 11, right? Clear out denominators. 11, 7, negative 5. But what did we get last time? Negative 11, negative 7, 5. So they're all just scalar multiples of each other, it looks like. Let's try it one more time, where I redefine this to be a, b, c. And we're going to see what happens here. So full disclosure, I've crashed this thing before trying to do this, and I've never really done it in this form. So I don't know. Let's see. I mean, A, B, C, right? So 2 equations, but 3 on it? I don't know. Do this. Okay, so all right, here, such that this is true. And then I'm going to clear out times 5. Look at that. So when I did it in very general, A, B, C, I still got negative 11, negative 7, 5, but then just times C, right? Where C is some non-zero constant. If I know what C is, I know what A is, I know what B is. This is really interesting. So there's a generalization that we can get. So maybe I should have written these down, which I did not. So this was the first one. So negative 11. So I'm going to say that u, okay, I'm handwriting these. So u is negative 11/5, negative 7/5, 1. And then the second time that I did it, I think that u was positive, positive, negative. I think 11/5, 7/5, negative 1. Then when I did this in general, I got that u was equal to, so there's a c in there, and I think I'm just going to go with that. I'm going to say it's negative 11 c over 5, negative 7c. So I'm writing this. And then c. So we got it in terms of c. Really interesting. So it looks like it doesn't really matter what number we choose. We want a non-zero, so c shouldn't be 0 based on this generalization that we found. But what is happening here? So what's happening is that we're solving a 2x2 system with 3 variables, right? So 2 of them are going to depend on the third, right? It's basically like solving parametric equations where you have too many equations, too many unknowns for the number of equations that you have. So we get it depends, right? It depends on this value, or I mean, we could have multiplied through by negative 5/7, and it'll depend on the j component, multiply through by negative 5/11, and it will depend on the I component, the I, j, k, the x, the y, the z. But they're all scalar multiples. That's really interesting. So what we would rather do, rather than have this particular thing where we have to like solve it, we want a generalization. So what we do is we define something called the cross product. So if we use something called the cross product, which we're going to talk about in a second, we will all get the same vector every time we do this process. So you're not just choosing this as 1 and this is 1. You're not even really doing this. What we're going to do, or basically you're doing this, but I think you're kind of letting c equal 5. And how do you know to do that? Well, the process is going to be related to it's related to one particular thing, which is the determinant of a 3x3 matrix. Is going to be the convenient way of remembering this. So if we have a 3x3 matrix where we have, I put row C here because this is going to become something later. You have A's and B's, right? These are your vectors essentially. Vector, vector, vector. So the vector has A1, A2, A3. This vector is B1, B2, B3, so on. This 3x3 determinant is C. So let's see. It's C1, and then you pull out this A2, A3, B2, B3. And then minus. The minus is what you're going to forget. Everybody does. It's going to be C2. And then after you do C2, you pull out this and this. So you delete, basically you delete the row and column and you write down what's left. A1, B1, A3, B3. There you go. Then it's plus, so it's C1, the thing, minus C2, the thing, plus C3, its thing. So if you've never done these before, I mean, I guess you're doing them now. I don't really have any like sage advice on that other than like, I wish you had done them before. So we cancel out the row and column. We're left with this, and there you go. Okay, that's a 3 by 3 determinant. But then what does this mean? Well, this, hopefully you're recalling, is A2, B3 minus A3, B2 times C1, then minus A1. So it's diagonals, A1, B3, and then minus A3, B1, and then that's C2, and then plus A1, B2, so diagonal, and then minus diagonal. So it's A2, B1, and then C3. This is a 3 by 3 determinant. Hopefully you've seen a 3 by 3 determinant before because we are about to use them a lot. 2 facts about 3 by 3 determinants. 1, if 2 rows in the array of a determinant, so if 2 of these rows are the same, then the value is 0. How could it not be, right? Change this to an A1, an A2, and an A3. This becomes A2, A3 minus A3, A2. Obviously 0. That's going to happen down the line. All of those are just going to be 0. So if 2 rows are the same, you're going to get 0. That's going to save us a ton of time. If 2 rows are interchanged, then you actually just multiply the value of the determinant by -1. Now to see that, imagine you switch these up here, right? So now it's going to be B2, A3 minus B3, A2, right? So basically these switch, and that means that you've changed the sign, right? So if this was like 5 minus 4, now it's 4 minus 5. That's the opposite. So if you switch 2 rows, you change the sign. That's actually going to be really important for something that happens. So they feel out of left field. They're not, and you can confirm any of them by just like doing it. And you will see that if you make 2 of them the same, you get 0. If you swap them, you change the value. Here's a definition of a cross product. So if we have U and V using all of our appropriate subscripts, then the cross product U crossed V is defined, and this is super annoying. It's U cross V is, so we have the 2 by 2 determinant of U2, U3, V2, V3, I minus J, U1, U3, V1, V3. Now go up and compare this. Does this not look an awful lot like this? I think it does. It's exactly the same. Nobody can remember this. Well, no, everybody can remember this. Nobody can remember this. This is the expanded form. I don't know if anybody has that memorized. Sometimes when you're like programming things, you'll like type that in just to like have it in particular. Like, it's very annoying. Here's how you're actually going to remember it. So this is how we are going to take a cross product of 2 3-dimensional vectors. U cross V, you go I, J, K. Those are your standard unit basis vectors. I is 1, 0, 0, J is 0, 1, 0, K is 0, 0, 1. I, J, K. And then the first vector, which corresponds to this. So the order is really important because if you switch 2 rows in a determinant, you change the sign. The end result of a cross product is a vector. It is a vector that's orthogonal to the 2 vectors that you are crossing, and it's a big deal. So I'm going to stop this here. I'm going to come back in the next video, and we're going to actually find some cross products, and we will go from there. So I will see you in the next one.